So I'm going to try to arrange for a group work session on some of these inverted lectures. Would Monday evening work okay for everybody? Huh? After like 6:30? I could probably do that. No, after 6:30? Before 7? 6:30 is before 7. How about we say 6, and then people can kind of come and go. So keep an eye out for the email. I haven't got a room yet, but we'll do that. But bring your inverted lectures with you. I have no agenda at this. You all will just get up and do some practice on the board, and I'll help you work through those as much as we can. So we got to get into chapter 13, where we're going to start talking about conjugated systems. And so today we're going to talk a little bit about allylic radicals, allylic cations, and resonance rules, which you need to read on your own. At this point, you all know your resonance rules fairly well. Okay, so I don't need to spend a whole lot of time on it. But on Monday in class, I'm going to give you a little bit of a not-for-credit quiz on resonance. So we'll have some questions that we go through to see how good your resonance rules have stuck with you. Okay, so we'll be looking at that then. I'm also going to pencast some problems from chapter 12 this weekend. I'm going to pick probably 3 or 4 questions from chapter 12 that I'll work on pencast and I'll post into Blackboard for you to go and look. What I would suggest that you all do is I will announce which problem I'm going to do in the book. I would suggest at that point you pause it, work the problem on your own, and then watch how I solve it, okay? That'll be probably the best way to go about doing it. So there'll be 3 or 4 of those placed in Blackboard this weekend at some point, okay? So all of these systems that you're looking at are conjugated. What do I mean by conjugated? What do we mean when we say something's conjugated? You all intuitively know what I mean, right? But now describe it to me. What does it mean for something to be conjugated?
It's like it comes from something, it's like it resembles a
One of these days I'm going to write a book on Matthew Hasslerisms. I think he's well on his way to being a politician, I think. Huh? Oh, so he's on his way already. All right, good. What do I mean by conjugated?
Oh, this is flipped.
Huh?
This is flipped.
What's,
It's not literally the same thing now.
which one?
Almost all of them. Aren't they all like the same thing?
Are they?
Well, it looks like it.
They look like they're flipped, but remember in resonance we can't,
Just move it.
I could, but remember in resonance rules I can't move atoms, right?
Yeah.
So this atom is this atom. This atom is this atom. This atom is this atom, because I'm using my resonance arrows here, right? You can consider it to be on a 2-dimensional plane right now. Okay. Conjugated systems, what can I do for conjugated systems that I can't do for isolated pi systems? What is all up there? Resonance. I have the ability to draw multiple resonance structures of conjugated systems. What that means is that the pi system, the pi bonds, okay, that we're looking at, or the p orbitals, are all communicating with one another. They're overlapping. That's what we mean by conjugated, okay? And so when we see a pi bond, like this alkene, connected to another pi bond by a sigma bond, those are in conjugation with one another. We can draw resonance structures. I can push the electrons from here to form a double bond between these 2 carbons, and I can break that weak pi bond and put those electrons on that N carbon. The whole system is talking with each other, okay? I can do exactly the reverse. I can push the electrons this way and get this resonance structure, right? Of those three possible resonance structures, which one's the major contributor and why? That's right. We don't have charge separation. That is the major contributor to the overall resonance hybrid. However, does that mean the other ones we can just ignore? No. That's exactly right. And we'll find out in this chapter that these resonance structures have a lot of importance to us. What about the second one, the allylic radical? I can only draw two resonance structures. What do those resonance structures tell me? For example, if I went into a polymer science lab and they generated that radical to make a polymer, right? What would those resonance structures tell me? Which carbon of that allylic radical, or carbons, would form bonds with other monomers? Either side, but never the middle, right? Because it's the two terminal carbons that actually bear the free radical. And in the hybrid, we would say that both terminal carbons bear some radical character, right? We can't adequately describe that using a single resonance structure, so we draw multiple ones, and the hybrid is somewhere in between. The allylic cation, same sort of thing, and the allylic anion. All of these systems are more stable because we can draw multiple resonance structures, right? So conjugated systems are typically more stable or enhanced stability, okay? Now, if you think about the allylic radical example, the picture that you see there really only partially tells us the story, right? I got two carbons with a pi bond and then a single carbon with a single electron sitting on it in what kind of orbital do you think? What would that electron, that single electron, be sitting in? What kind of orbital? S orbital, P orbital, sp3, sp2? It would be sitting in a P orbital. Why would it be sitting in a P orbital? Okay. Okay, right. And so in reality what we have are three P orbitals on that allylic radical system, right? And each one of those bears an electron. Two are paired and one is not paired, right? That's why you get the pi bond. But we could easily draw the pi bond here, or we could easily draw the pi bond there. And that's why we have these two resonance structures, okay? The overall resonance hybrid sometimes is drawn like this. It's a house. It's kind of a roof line. Okay. What is that telling us? What is that depiction telling us? That's right. That double bond can actually be over the entire system, and that radical is actually over the entire system, right? But it only exists at the ends. We know that from the resonance structures, right? So that's what that's telling us. So sometimes you'll see it drawn like that. Now, we've talked a little bit about allylic substitution and the allylic radical in Chapter 10 when we talked about free radical chemistry. And we know that if Rose comes into the lab and she takes propene, a simple alkene, right? And she takes, let's say, bromine, and she adds bromine to the alkene, she just gets halogen addition across the carbon-carbon double bond, right? And she ends up with the dihalide. Nothing surprising there. That's electrophilic addition, okay? However, if she comes into the lab and she does essentially the same experiment, but she keeps the concentration of bromine really low and she heats it up really high, she finds that she doesn't get addition across the carbon-carbon double bond. That must mean that the mechanism is different, right? In the top case, describe the mechanism for me. What's the first thing that forms? What forms first, Sam? If I take a halogen like bromine and I put it in with an alkene, what do I form? Okay, but how? What's the first intermediate that gets formed? Jamie? The bromonium ion. That's exactly right. We get that bromonium ion plus the bromide, which then attacks the bromonium ion, right, to give us the dihalide, or attacks the carbon of the bromonium ion, right? So that's the mechanism. What's the mechanism for the bottom reaction? It's a free radical mechanism. That's exactly right. Okay? And so we have that free radical chain mechanism that occurs in the bottom example because we're at really high temperatures and we keep the halogen concentration low. And so we can do free radical allylic substitution because we know that that allylic radical is going to be stabilized, right? And we can promote that pathway under certain conditions. Okay? So here's an example taking propene, chlorine. All free radical reactions have what steps? Initiation, propagation, and termination. How do we identify an initiation? No radicals on the left, radicals on the right. Very good. So the first step that we see up there is the initiation step where the chlorine molecule, right, is either being heated really, really high or we're using strong UV light to break that weak chlorine-chlorine bond and we get radicals. Once we get radicals, we're initiated and we go into a free radical chain process. And so we can have how many propagation steps? A lot. We can have as many as we need, right? And so in the first propagation step, remember the chlorine radical abstracts a hydrogen atom from the allylic carbon. Why the allylic carbon and not the other carbons, Gabby? That's true. Different hybridization. And what else? Okay, that's good too. That's true. What else? If I abstract one of these sp2 hybridized hydrogens from, what kind of, do I end up with a stable radical? That's right. But if I remove one of these hydrogens, I get an allylic radical, right? And that's stable. So that's why we see that process occurring. And so we get HCl plus we get the stable allyl radical. And now the allyl radical comes in and reacts with the chlorine. We end up with the allyl chloride product, and we get chlorine radical. And what happens to that chlorine radical, Brienne? What happens to this chlorine radical? That's right. It comes back up here in this part and reacts again to continue the... And this chain continues until we start to run out of starting materials, right? Once we start to run out of starting materials, then what happens? We start to go through termination processes, right? So the concentration of radicals all of a sudden jumps up to really high concentrations, and they start to react with each other. So even though it's not shown here, give me some examples of products that you might expect to see from termination. We might expect to see 2 chlorine radicals come together and give Cl2. What else might we expect? Yep, we could have a chlorine radical and an allyl radical come together and give us the product. What else could we have happen? We can have 2 allyl radicals come together and give a pure hydrocarbon, right? And if we did a very careful analysis of the reaction mixture, we would find those things, okay? But if we'd run our reaction well, we're going to get mostly the allylic chloride or the allyl chloride. And so that's how these chain processes occur, okay? But it's because of the stabilization of this conjugated system. That's why this occurs the way that it does, okay? Now, if we look at radical stability, we know that radical stability follows very closely with what in terms of trend? Carbocation stability. And why, Brian? Why would a radical follow about the same stability order as a cation? What do they share in common? Not an extra electron. They have an unfilled octet. That's right. So a carbocation is electron deficient, and a radical is electron deficient, right? And so they should follow the same order, but is it going to be the same magnitude? No. Which one is more stable, the radical or the cation? The radical is more stable than the cation. That's right. That's right. Cation's missing 2 electrons from the octet, whereas a radical is only missing 1, right? And so what you see in terms of stability follows exactly what you'd expect for a carbocation. Methyl being the least, primary, secondary, tertiary, and then the allyl. And why is the allyl more stable than a tertiary? Because of resonance. Remember, resonance trumps. Now that we're talking about politics, right? It trumps the substitution because of the resonance stabilization, right? And so if we look at it, you can see kind of what the energies are. This has the lower energy, more stable. Okay? So we see considerable stability increases due to conjugation and resonance. Okay? Now you'll recall that one of the ways in which we can keep the halogen concentration low is not to use bromine, molecular bromine. We use NBS. Okay? Can anybody tell me what are some of the advantages other than keeping the concentration low of NBS versus molecular bromine? We talked about it in 255. Bromine's actually a liquid, but it's a pretty, it vaporizes pretty easily, so you do get a lot of vapor. Okay, chlorine's a gas, but bromine is a liquid that puts off a lot of bromine vapor, which is toxic. What were you saying, Gabby? Oh, Bree, what were you saying? That's right, it doesn't add anything to the alkene because we keep the bromine concentration low. Anybody can think of anything else? Cheaper to work with. I haven't done a cost analysis on that one. Could be.
Is that a solid NBS?
Ah, there we go. It's a solid. Yes, it's a solid. And we can go to the scale in the laboratory and easily weigh it out. It's a nice white crystalline solid. You have to wear gloves, of course. You have to wear your safety goggles, but you don't have to wear a respirator. It doesn't put off bromine vapors that are toxic. Okay, so it is a safer form of bromine, if you will, than molecular bromine. If we were to work with molecular bromine, it's a liquid. We'd have to pipette it out in a hood, making sure not to breathe any of the bromine vapors because they are quite toxic. And so it's a lot easier to work with. And the fact that NBS breaks down slowly to give bromine, okay, goes along with what Brienne was telling us about the fact that it won't add to the alkene like bromine would because we never have very much bromine around as NBS decomposes. It keeps the concentration quite low, okay? The way that this reaction works, you would take your alkene that has an allylic carbon with an allylic hydrogen. In this case, we're using cyclohexene. You would have your NBS, and you would put all these things into solution, and you would shine a bright light on it. We have a sun lamp, basically, in our lab that we use. It's a 450-watt mercury discharge lamp. It is in its own hood that is blacked out so that you never want to look at that. It will tan you in like 2 seconds. It will burn you in like 4. It's pretty intense light, okay? But what happens is the nitrogen-bromine bond turns out to be fairly weak. You generate a bromine radical plus a succinimide radical. That bromine radical then comes in and abstracts a hydrogen atom from the allylic carbon, one of the allylic carbons. There's 2 here, right? You get the allylic radical plus HBr. The allylic radical then reacts with the low concentration of molecular bromine that's present, which comes from NBS. And you end up with the product that you want plus bromine radical, which then continues the propagation steps. Okay? So, how do we get molecular bromine from NBS. I just have it written there, Br2 from NBS, as if it just magically happens. What do we know about magic? It's good for Harry Potter movies, bad for science, right? What happens to what?
Well, I thought it just did that.
That's what happens in the top step. That's the initiation. But how do we get Br2? It's possible for that to happen, but that only would happen at termination steps, right? And obviously we're getting the bromine in a propagation step. So how would we account for that? They could. The two nitrogen radicals could make a termination step, but that's still not going to give us Br2. Where's the other bromine that I'm not taking into account in that propagation step? Where do we have another bromine? Just look at the propagation steps. Where do we have another bromine? We know we have a HBr. I haven't taken into account HBr at all, right? I've just assumed that it's a byproduct. But it actually reacts with NBS to form bromine. That's how we get it. So it turns out that HBr is a strong acid, right? And notice that HBr, it's generated, but it never adds across the double bond because it doesn't stick around very long. What happens is HBr will react with NBS to actually protonate the nitrogen, we believe, okay? Which is kind of odd. And you end up with this nitrogen with a positive charge. That's a pretty good leaving group, okay? Bromide is a good what? Nucleophile. So you have the bromide nucleophilically attacking the bromine, and the nitrogen that's positively charged leaves, and you end up with what's known as succinimide plus molecular bromine. That's how we get the molecular bromine out of this reaction. And that step is slow, and that's how we end up keeping the bromine concentration extremely low. Once it's generated, it's consumed immediately. And so the bromine concentration at any given moment is really close to zero. The nice thing about this reaction, the solvents that we typically run the reaction in, succinimide is not very soluble, and it precipitates out a solution. And that's how you know that the reaction is occurring. You will see this. NBS will be soluble, but the succinimide itself, for whatever reason, is insoluble in things like carbon tetrachloride, and it just falls out of solution as a nice crystalline product, and you know that the reaction is working really well, okay? So we can generate bromine from NBS and HBr. So it's using that byproduct from that first propagation step to actually generate the bromine that's needed, okay? Molecular orbitals. We are going to talk about molecular orbitals quite a bit in this chapter, but the nice thing is we are only going to use what I call frontier molecular orbitals. Remember in Gen Chem when you had to draw those orbital diagrams? How bad did it make your head hurt? A little bit? A lot? Quite a bit, right? You were taking all the orbitals in a molecule and building the entire molecular orbital framework, right? It turns out that most of those molecular orbitals that you all dealt with don't matter. Don't matter a bit. Okay, they're too low in energy. They're too stable. What we're interested in are the orbitals that are high in energy, right? Those are the ones that are going to react. And we call those to be the ones at the frontier. So notice, in this particular system where we're looking at an allylic system, and let's just take the allylic radical as an example, what orbitals are we using to take into account? Are we taking any of the s orbitals into account? What orbitals are we taking into account? The p orbitals from the pi system, because they are the higher energy, right? So we're ignoring all these lower level orbitals. And so we know from the previous slide that each one of these carbon atoms has a p orbital, right? I just showed you that. So now I've got 3 p orbitals that are the highest in energy. Those are the only ones I want to pay attention to. Now, if I take 3 p orbitals, how many molecular orbitals do I have to get? It's up there. If I take 3 p atomic orbitals, how many molecular orbitals will I get? 3. Remember, orbitals are conserved. If I take 3 p orbitals, I've got to get 3 molecular orbitals. Okay? These 3 frontier molecular orbitals. So we know that a p orbital has signs to it, right? And so we can have a p orbital, and we'll just shade one side and leave the other lobe unshaded, right? How many different ways can I combine those 3 p orbitals to get 3 new atomic orbitals? Well, I could have a situation where all 3 p orbitals on the molecule have like signs on the same plane, same side of the plane, right? That's that one there at the bottom. That's the pi bonding orbital. Okay? How else can I arrange these? I have to have a node now, right? As we go up in energy, we have to generate nodes. I can have that as a bonding orbital, or excuse me, non-bonding orbital. A node? It is a place of no density. Just like that is a node. So we have a change in sign. So we go from unshaded to shaded. That's the node. There cannot be an orbital here, or no orbital contribution at a node. I just have to make combinations of them. I have to have 3 molecular orbitals because I took the 3 atomic orbitals. This is a single orbital. So I've taken 3 and I've made 1, 2. I've got to make 1 more, right? There's the third one. I can have a combination where I have 2 nodes. And that's what the top one describes.
So is there just no third orbital in that second?
No, there's no orbital contribution here. It's on both on the ends.
And so
Now don't think of these as p orbitals. This is a molecular orbital. But it looks like you have p orbitals on the end. But this is a single orbital. So I took 3 p orbitals and I combined them to make 3 atomic orbitals. The lowest energy one will have no nodes. That means there's going to be orbital contribution on each carbon. The next highest one will have to have a node, and the easiest way to do that is to have a sign, node, opposite sign. This is a single orbital. And then this is an orbital where I know I have to have 2 nodes, and the way that I make those combinations is like that. And so you end up with 3, or you start off with 3 p orbitals, you end up with 3 molecular orbitals. Okay? Pardon? Do all these? Yes, they exist all. Yes. Okay. So, if we're talking about an allylic radical, we're going to put 2 electrons in the bottom and 1 in the middle, right? This is a non-bonding orbital. So, this tells me that this electron does not form a bond with anything because it's in a non-bonding orbital. But I can look at the resonance structure and tell you that, right? Because it's a single dot on a carbon atom. Okay. Now, if it's a carbocation, what would if it's a allylic carbocation, what would the structure look like? Same molecular orbitals, right? But what would be different? Karina. What would be different for an allylic carbocation? No electron here, right? That would be my cation. How about for a carbanion, an allylic carbanion? I'd have 1 more electron right here. I'd have a negative charge here and here, right? Or a partial negative here and here, right? But the molecular orbitals look identical. It's just the number of electrons that I put into them. What would happen if Matt came in and he wanted to make an allylic dianion where there's 2 negative charges on an allylic system? Would you predict that to be stable or unstable? You would predict it to be unstable, and why? Okay. The allylic anion would have another electron here, right, and a minus charge. To get a second negative charge, where would I have to put the next electron? Anti-bonding orbital. Is that a good thing or a bad thing? That's a bad thing, and so it becomes unstable, right? So getting an allylic dianion, I won't say it's impossible, but it's harder to do. It's less stable because of the orbital diagram, okay? So the good news is, if you can figure out how to take these dumbbells and put them in combinations, you can build the molecular orbitals that you need. Because organic chemists have figured out you don't really have to hurt your head doing this that much. It's not like putting together the molecular orbital diagram for carbon monoxide that you all had to do, or molecular oxygen that you all had to do, where you're looking at the s orbitals and the p orbitals and everything. We're just looking at the frontier molecular orbitals, the things that are highest in energy, because that's where all the chemistry occurs for an organic chemist, okay? Makes life a lot easier, okay? And so there's the description of the allylic cation. We won't go through that too much. We just talked about it. And so I think for molecular orbitals for today, that's enough hurting of your head. But I want you to think about it this weekend. But before we go, I want you to think about these problems. So we've got about 8 minutes left. Exactly 8 minutes left. Get together with your teams and work on this. So whatever product A is, that's what you're using here, okay? Huh? This can just be in your notes. I'm not going to take this one up. Uh-huh. Do I go to my office on Fridays? I'm in my office all the time. Huh?
Did you mean to leave out, like, there should be like a third line?
No.
Like, how do you...
A plus formaldehyde gives B, and then that's the end of that. And then the next reaction is acetophenone plus whatever you need for C to give the final product.
All right, so we're not... Okay.
Yeah. What's going to happen in the first reaction? Pardon? You're going to get a Grignard. That's right. So you need to draw that Grignard reagent. Pardon?
What's the reaction rate if you're using like a chloride ion or a bromide?
Chlorine is slower.
It's slow, like
Yeah,
how much?
a lot. It's just that the chlorides are a lot cheaper to buy, so people will sacrifice a little time to. Yeah. The iodides are the fastest, but they're also the most expensive to purchase. A is the product A. It's your Grignard reagent. It's this. So A plus formaldehyde, what will that give me? Okay, we're going to insert the magnesium between this carbon and this chlorine, right?
So what do I do with this diether?
Diethyl ether is just your solvent.
Oh.
Well, I'm sorry, Brian. Think about how that Grignard reagent's going to behave. How's it going to behave? Not as CH3 minus. C minus, yes, but we don't have CH3, right? We have an aromatic ring. So it's going to behave as benzene minus, right? There you go. And you get a primary alcohol, that's right. So with formaldehyde, you can get primary alcohols. Whereas if we used a regular aldehyde, what would we get? Not a tertiary, a secondary. With a ketone, we would have gotten a tertiary. No, it's not. There's two hydrogens there. Yep, it's formaldehyde, not acetone. No, after that you're done with B. Yep. Where?
So this one has the O minus. We're just wondering where we will get the hydrogen.
Assume standard workup where needed.
Okay, gotcha.
So after you get that O minus, if you're not doing anything else with it in the second step, you can assume you just work it up with water, maybe a little mild acid or something like that. Almost always you dump organic reactions over water at the end. An ethyl Grignard? Yep. Be careful. 1, 2, 3 carbons.
Oh, no, wait.
Make sure you count your carbons. All right, everybody. I want you all to have a good weekend, and pay attention to the email for the PinCast when it's available in Blackboard, and for the location and times for our Monday evening help session. So have a good weekend. Happy Valentine's Day.